especially for the opportunity to be giving the first kind of Monday morning talk, and also tomorrow morning a follow-up to this one. And given that there's two talks, and given that there's something like a scary word, a scary German word in this title here, I really want to start off slow and kind of I'd rather have everyone now following along and maybe even got a little bit bored rather than just presenting too many technical details that are not so relevant for the conceptual aspects of what I'm going to say anyway. I want to start out with just a good deal of motivation, some kind of examples, and explaining the first kind of Vergleichsstellensätze before getting to my own results. And so as far as the motivation is concerned, let me start with, since this is a workshop on tensors, with the original motivation that had also led Strassen to develop his first Vergleichsstellensätze, and that motivation is coming from tensors. And by the way, I mean, please feel free to interrupt me at any time if anything is unclear. As I said, I guess it will be part of just taking it slow. So suppose that we have a tensor, so defined over any field F, and everything is in finite dimensions. And let's say we just have 3 tensor factors, but this is just because to keep the notation simple, I mean, this whole thing we can do with any number of tensor factors. So let's say this is an element of f to the j, tensor f to the k, tensor f to the l. Then we may be interested in understanding what is its rank. I imagine that there's been quite a lot of discussion about tensor ranks and so on. So let me just write down the definition again very briefly. So the smallest natural number n, such that we can write the tensor as the sum of elementary tensors, right? So which there exists a decomposition in this form. So then we have some elementary tensor here. Let's call it xy tensor yi tensor zi. So this is one interesting quantity to study, and I guess in general kind of also difficult to understand quantity. But what's of interest then, especially in the more complexity theory applications, as far as I understand, for example, for the complexity of matrix multiplication, would be something more like the asymptotic rank. So if we take a tensor power of t, so that correspondingly we get a larger tensor, then what is the rank as the tensor power goes to infinity? How does that rank grow? And well, of course, it's a known phenomenon, and I guess most of you will know this much better than I do, that the rank is in general not multiplicative. So this means that this will grow, may not just be the nth power of the rank of t. I mean, there's 2 ways also, just to be completely clear. I mean, there would be 2 ways to take this tensor product or tensor power, right? We could then consider this as a tensor of something like, I mean, 3n factors, but this is not what I mean here. Here, what I mean is just to take the sort of Hardy-wise tensor product and to use kind of more kind of information terminology. Okay, I guess that's all pretty basic so far, right? Okay, so a more general question that we may be interested in is under what conditions can we obtain one tensor from another using something like what corresponds in the quantum information applications to something like SOLCC operations, I think. So when we have 2 tensors, how can we obtain one from the other using just linear maps that operate on the individual tensor factors? When they're linear maps at G and H such that S can be written as F tensor G tensor H, and that applied to T. So clearly an obvious necessary condition here in order for this to be possible is that the tensor rank of S is at most the tensor rank of T. So it's just applying these sort of local operations here clearly cannot increase the tensor rank. But in general, I mean, this is not a sufficient condition. And so just to have a more concise notation for this, I'm just going to write S less than or equal to T. For this relation, this notion that there exists such linear maps F, G, and H. And also I'm not assuming that S and T live in the same dimensions here, right? These can be different. And so this is a preorder relation, I mean, a reflexive and clearly transitive relation on the set of tensors of arbitrary dimensions. And then actually the rank can also be phrased in these terms, namely saying that T should be less than or equal to something like the sort of maximally entangled tensor corresponding just to the sum over the elementary tensors given just by tensor products of the standard basis vectors, let's say. Okay, so here we can also ask a problem that is analogous to this asymptotic rank, and in fact generalizes this asymptotic rank. Namely, well, if this does not necessarily hold under what conditions does this hold asymptotically? So when is S to the n less than or equal to T to the n for sufficiently large n? Now, okay, we could ask this, I guess, in two ways. Does there exist an n, or does this hold for all sufficiently large n? And here I'm a little bit imprecise about which of these two options I mean. But also, I mean, we're going to see that these kinds of questions are basically equivalent. Okay, so now let's try to analyze this sort of situation in algebraic terms. Just what is the kind of structure on the set of tensors that we're actually using here, and how can we formulate this problem just pure in terms of that abstract structure, and then how can we maybe apply some theory of this abstract structure in order to address these kinds of problems. So, well, the abstract structure that we have here is on the one hand a preorder, and on the other hand our tensor product. So these kinds of thing we have, meaning a set of tensors with a binary relation, a preorder relation, and then the tensor product as a binary operation. Well, these make the set of tensors into what one can call an ordered commutative monoid, right? Meaning that monoid, meaning that the tensor product is associative and has a neutral element, and a commutative monoid, meaning that the tensor product is commutative at least up to preorder equivalence, which I'm implicitly sort of taking the quotient here by the when two tensors are ordered in both directions, then I'm kind of identifying them, and so then these classes of on these classes the tensor product is associative, commutative, and has a neutral element given by just basically the non-zero tensor that is an element of F, tensor F, tensor F. That will be the right neutral element under multiplication, or let's just say 1, tensor 1, tensor 1. And well, the nice thing about this, what order commutative monoid means then is that I also mean that this binary operation is compatible with the preorder structure, meaning that it's monotone. So if I have three tensors S, T, and U, and I have s less than or equal to t, well then we also have that s tensor u is less than or equal to t tensor u. It's pretty straightforward to see, because if we have this for some at g and h, well then we just get this if we just use f tensor identity, g tensor identity, and h tensor identity. Okay, so now we can ask ourselves, well, this kind of question we can formulate for any order commutative monoid. When we're given then elements s and t, under what conditions does this sort of thing hold? And maybe we could hope that there is some sort of, well, duality theory that tells us this holds if and only if we have some kind of simpler inequalities that are simpler to analyze. And while that is indeed the case, and before I go into the details of this, let me just say this is a little bit, or very much in the spirit of quantum information, where people study resource monotones. This is basically a setting of resource theories. Things like free energy, thermodynamics, entropy kinds of things. We're interested in when does this sort of relation hold? And this is basically like the existence of an asymptotic resource transformation. When can you go from many copies of T to many copies of S? And well, this is the sort of thing that people analyze using resource monotones. And so one would ultimately want to have necessary and sufficient conditions in terms of such monotones, right? And that's basically what this whole thing, what this whole story is about.
So you probably said it already, but I missed it. Commutativity refers to what?
Just that the tensor product is a commutative binary operation on the set of tensors, at least modulo the preorder equivalence. So that I have S tensor for any S and T, we have this inequality, I mean, the inequalities go both ways. So for order commutative monoids, I don't want to go too much into details of this because I want to move on then to the ordered semirings. But it turns out that for the order commutative monoids, there actually is such a corresponding separation theorem, which applies and gives sort of necessary and sufficient conditions for this to be the case in terms of resource monotones. And what this amounts to is basically the hanbanoff theorem. You can state and prove hanbanoff theorem purely for additive maps on an order commutative monoid. I mean, it's usually presented as a theorem on vector spaces or norm spaces or ordered vector spaces, this sort of thing, but it's actually somehow can be phrased and proven at the level of generality of order commutative monoids under a suitable additional assumption. Okay, so then this is going to give right, this is kind of a theorem. I mean, this is not so difficult because the hanbanoff theorem itself is maybe not so difficult. That we have that whenever this holds, then and this is kind of the trivial direction of the theorem, and then I'm going to write down the more difficult direction that actually requires the hanbanoff theorem. That then certainly phi of S is less than or equal to phi of T for all additive monotone maps going from our order commutative monoid of tensors to the reals. So far this is the trivial direction, and so here you can take things like, for example, any bipartition of the tensor factors, and then look at a rank across that. And well, I guess you should then take the logarithm in order to make it into an additive map. Additive meaning that phi of S tensor T should be phi of S plus phi of T. So this kind of suggests that we should be looking at these kinds of additive monotone maps. And now the question is, what about the converse? Are these inequalities sufficient in order for us to conclude that. And yeah. Yeah, please.
Checking my understanding. So Z is not an ordered commutative monoid because you can take two negative elements, multiply them together, so it gets something positive.
No, that would still qualify. So by ordered commutative monoid, I mean, it could as well be a group, an abelian group. So an ordered abelian group is still an example. So just a commutative monoid together with a partial order relation such that addition is monotone. Oh, sorry, what am I saying? So no, sorry. In a group, it doesn't work unless, yes, wait, yeah, you're totally right. So here for the integers, okay, we could consider them under multiplication or under addition as the monoid. But as long as the binary operation is monotone, that's the important condition. Yeah. Sorry. Yeah, I wasn't actually intending to, let's say, talk much about ordered commutative monoids because then we're going to get to the semirings. So sorry about the confusion, but the integers, yeah, under addition would not count, and neither under multiplication, right? Because then we can reverse inequalities. No, what am I saying? No, and under addition is fine, right? And addition is monotone, but multiplication is not.
That's what numbers would be. That's the simplest example.
Right. Yeah. Yeah. Okay. So the hanbanoff theorem actually for the tensors and also in general under some kind of niceness conditions on the ordered commutative monoids gives us something like a converse, a kind of partial converse. Namely, if all of these inequalities hold strictly, then we can conclude that this holds. So for all such phi, then we get that this holds for all sufficiently large n. That's now what I'm going to get to next. Exactly, we cannot really check all phi in the sense that they're just a lot of these, and we cannot really hope to, at least just from this theorem alone, you cannot really check all such phi. It's not very practical. So that's why exactly the sort of deficiency of this thing, and why now I want to kind of go to the level of the semirings. Yep.
You said some kind of non-triviality of this phi, or some normalization? Or
no.
Otherwise, I could take the zero map.
Yes, right. Sorry. For all non. Yeah. For all non-zero phi. Yeah. So basically, I'm assuming basically that there is an order unit in the order commutative monoid, and then we can normalize it on the order unit. But okay, so then as was already just pointed out, this kind of thing is actually not all that useful. So this is difficult to apply.
Sorry.
Yeah, sure.
Don't we need to be a little more precise? So then, I mean, by saying like what the value maybe is on a simple tensor, because otherwise now I could imagine like the map that is, I could take two maps and they're like the same map, just differ by a factor.
Yeah, sure. I mean, you can
somehow, but then somehow the converse wouldn't kick in, no?
I mean, we can impose a normalization if we want to, but here.
You don't think we need?
No, right? I mean, if this holds for some phi, then it also holds for every non-zero scalar multiple, right? Or a positive scalar multiple. But yeah, actually, I have to admit that as far as the formal statement here is concerned, I haven't prepared this very well, because the actual things are going to be the ones for the semirings. Those are going to be the results where I really want to be precise, and those are going to be the more useful ones than this. So this is just supposed to be kind of an introduction and the thing that's actually not useful. So maybe let's not spend a lot of time on this. Although so this was more like a a motivation. So I hope that conceptually it's there. Okay, because how do we classify all these five? So yeah, it's kind of that kind of suggests that this sort of result is just not so useful. But this is where now basically Strassens Vergleichsstellensätze comes to the rescue, and basically his observation is that the tensors have more structure than what we're using here in the order commutative monoid. And although this structure is not relevant for formulating our problems, like things about the asymptotic rank or the asymptotic ordering, this extra structure turns out to give us a much more powerful theorem. And so what this extra structure is that, well, we not only can take tensor products of tensors, but we can also take direct sums. And well, that's part of the, I think, the title of this week's workshop, right? Direct sum theorems and dualities. So I think that, as far as I understand, that's where the title comes from. Okay, so tensors have more structure, namely direct sums. And if we take the direct sum of two tensors, what now I mean by this, or actually Strassen means by this, is that we sort of take, first of all, the local direct sums of the tensor factors. And then this is where the new tensor S direct sum T lives, right? So the local dimensions add up, and then we get this new tensor S, which is sort of has this kind of block form. So that corresponds in a sense to entanglement, right? If you just take a direct sum of two tensors, and you're basically creating like an entangled state. That's the same kind of construction. Is that clear, or should I write it down in more detail? Okay, good. And so now this satisfies that this direct sum, the tensor product distributes over its direct sums, right? So at least up to the preorder equivalence again, so kind of up to isomorphism of tensors. So let me just write this like that. So by here I mean that this is ordered in both directions. Okay, so yeah, and also we have that this direct sum is obviously again associative and commutative up to preorder equivalence, and has a neutral element just given by the zero tensor in 0 dimensions. So that means that tensors, and now this is where the kind of my formal developments really start. Tensors form, and I write down the definition in a bit more detail in a second, an ordered semiring.
Why isn't it just preorder?
Yeah, okay. So by ordered, I sort of now mean pre-ordered. But if this is a kind of annoying technical but ultimately irrelevant technical subtlety that we can kind of either take equivalence classes of tensors under the preorder equivalence, and then we get an actual semiring where all the equations hold strictly with equality, or we can say we just keep it a preorder. But then we have the issue that we cannot write equals here. Then we need to write something like order in both directions. And which of these options you choose is ultimately just basically a notational choice. And because in the end, it's just amounts to, when we take the quotient, that just amounts to using the equality symbol for preorder equivalence.
Excuse me once again.
Yeah.
What do you mean exactly by this direct sum?
So this is suppose that if S is an element of our tensor space, and T is one and another. So then J prime, K prime, and L prime. S direct sum T is going to be an element And well, this doesn't define it yet, of course, but an element of just to indicate how the direct sum works, that a tensor, the local dimensions add up. And the idea is that we just use kind of S when we kind of multiply these out. We use S on this direct summand, and we use T on this direct summand. So we could also try to, I mean, write this out in components. Then this basically just amounts to adding S and T up once we've included them in this larger space, right? Where S just lives on this part and T lives in this part.
So it's like S is a cube of numbers and T is a cube of numbers, and then you just put them as blocks on the diagonal. Just like you take the direct sum of matrices, just put them as blocks.
Yeah,
So
thanks.
rows and columns. Yeah.
Nice. Yeah, that's a good way of putting it too. Yeah.
You don't add any coefficients. Yeah.
Okay. That was is this one a blackboard too, or?
Yeah.
It just doesn't move. Can we write in here? Yeah. Good.
Yeah.
Okay, so now the protagonists really of my talk are order semirings, and just to already maybe preemptively clarify this, when I say semiring, I'm always meaning commutative semirings. I only consider commutative multiplication. It's often done also in ring theory, which just drops commutativity because in a context where everything is commutative anyway. So an order semiring is a partially ordered set, or as I said, you can also define it as a preordered set, which is how I've done it in the papers. But maybe partially ordered set is a little bit easier for most people to think about, together with now two binary operations, or so a semiring structure, meaning that so we have some kind of addition and multiplication, and then corresponding neutral elements. And well, just the usual, I mean, semiring, meaning that these are both, I mean, associative, commutative, and for me, commutative, with these neutral elements and such that multiplication distributes over addition. So just like commutative ring, except that additive inverses do not need to exist. And that's important, and we'll see kind of even examples where additive inverses do not exist and you cannot even embed them into a ring. And these are important for the theory itself. So yeah, and of course again the preorder and the semiring structure should interact in a nice way. And again, it's such that addition and multiplication should be monotone. So if we have some ordering relation, then we can add another element on both sides, and the inequality is preserved. Or you can also multiply by the third element A, and again, the inequality is preserved.
And this is what you talked about before, about the ring of integers, which doesn't.
Right, yes, exactly, yes. So if we take the integers with the usual order, then exactly.
So
right.
We don't have.
Yeah, although we could take the trivial preorder, then again, the integers would qualify, or well, any ring would qualify if we just take the preorder to be the trivial one. And in particular, my notion of order semiring, and this is actually important for some of the applications, does not have 1 greater or equal to 0. So I'm not assuming that the two neutral elements here are ordered. So maybe I can already kind of anticipate this, mention this now, what the examples are in applications where this would not hold. Imagine that we have something like probability distributions or quantum states. Well, unnormalized distributions or states as our semiring elements. In many cases, we also have direct sums. We have tensor products of these, right? So these would form a semiring, and then the ordering could be some sort of resource ordering. But typically, two such things, let's say two states, will be comparable only if they have the same normalization. You don't want to, yeah, in some sort of, I don't know, entanglement theory or something where you consider your states as resources. At least in some cases, you do not want to compare a normalized state with an unnormalized one, right? So that would mean that this inequality would not hold. And these sorts of cases, examples, I want to be able to cover, and so that's why I cannot postulate this.
Yeah, cases where you have you talked about cases
Yeah.
where you don't have it, they're not comparable. Do you have cases where
Absolutely. So, I mean, the general, let's say, generic examples of this, if you have an order semiring S, then you just reverse the order, and then it's again an order semiring. So if this holds before reversing the order, will be the other way. And also, if we take something like actually, so I'm also working on applications to majorization, where if you take sub-majorization, I think it actually satisfies the inequality the other way around, but I don't have the details offhand. I mean, there's a convention of how to define it, and somehow the convention that we found then more useful is actually the opposite one for the sub-majorization order. Okay, so yeah, let me wipe. How do I wipe? Okay, so yeah, let's look at some examples. So yeah, tensors. Maybe I don't need to spell that out again, but just to say what the neutral element of the multiplication is. I kind of had already mentioned that. I mean, it's just a one-dimensional tensor. Any non-zero tensor in tensor one dimensions. So let's just take this one. Yeah, as I already also said, for the integers, we can take any semiring and just equip it with the trivial preorder. Then we've got kind of trivially a preordered semiring in that sense. But I guess this example is not so interesting. So with trivial, so where only equal elements are ordered, we can take the natural numbers with the usual order, but not the integers, as we had already noted. Also, the non-negative reals under, again, usual order and the usual algebraic structure. And the non-negative reals also, again, as we'll see, play a distinguished role in the theory itself. And one of the nice things about this is that these actually form a semi-field. So any non-zero element is invertible. And then to see an example that does not embed into a ring, and which is still a semi-field, we can look at the tropical real numbers. And these also appear, as we'll see, in the theory itself. So the tropical reals, and so I like denoting these by TR plus, like this. And so this is defined, again, that its elements are the non-negative real numbers. And so I just now use this interval notation since I want to reserve the symbol R plus for the semiring. So here this just denotes the set of non-negative reals, and here the semiring with its usual structure. So just to clarify that distinction there. And so instead of usual addition in the tropical semiring, we just have max. So we add two numbers by taking the bigger one, and the multiplication and the order are the usual one. Yeah, and while multiplication distributes over taking the maximum, right? So this still defines a semiring. There's actually also something I called an Arctic semiring, but then we'll get to that tomorrow. As a kind of opposite temperature sort of thing. Okay, so now I'm actually getting kind of a little short on time, but let me write down Strassens Vergleichsstellensätze. And to do that, and then my generalization of it. And so to do that, I want to write 2 as just the usual 1 plus 1 now understood in the semiring. So in tensors, this would be so the semiring of tensors. We have that this element 2 is then just or let me write it out as kind of E1 tensor E1 sort of maximally entangled singlet state, right?
Oh,
3 tensor factors here. Then GS that state, I guess, is what a quantum information theorist would call it, up to normalization. Okay, so let me write down Strassens version. So this is Strassens Vergleichsstellensätze. And then also explain where the term comes from, Vergleichsstellensätze, afterwards. So here we have an ordered semiring S, and we need an additional assumption that kind of says that in some sense all its elements are bounded. And and also, first of all, we need that one is greater or equal to 0, which, as I had already said, I don't really want. But yeah, we'll get to that, how to get rid of that. And then boundedness assumption, which basically says that every element should be upper bounded by a natural number. So for all A and S, which should exist, and for reasons that we'll see then in my generalization of this, I'm going to take this natural number to be a power of 2. So there should exist some power k such that A is less than or equal to 2 to the k in S. Okay, and so now the statement, and here again we have the sort of duality as, or so some version of the duality that I had written down earlier in terms of the hanbanoff theorem. But now it's kind of a lot stronger. So the first condition is saying that phi of x is less than or equal to phi of y. And now for all phi's, well, now we have 2 pieces of algebraic structure. Previously, these were additive monotone phi, right? We basically took the, let's say, the tensor product of tensors, 2 additions, so additive in a sort of sense like entropy is additive, or the Renyi entropies are additive. And here, the condition is that this, well, really should preserve both pieces of algebraic structure. So this should be the semiring homomorphism to R plus. And of course, yeah, I should say monotone as well. And now here we have maybe a better chance to actually classify these. For tensors, as far as I understand, it's still really hard, but I'll show other cases where it's really simple and gives you something still highly non-trivial.
It's hard for tensors because it would determine like the matrix multiplication exponent.
Yeah. So yeah, but now the other condition that's equivalent to this one, which is now something about asymptotic ordering, and this is so Strassens version saying that x to the n. So now we're taking nth powers here is less than or equal to y to the n. For all, well, yeah, sufficiently large n, except that like this is not exactly true, but it's true. But a little bit of padding, if you want. We need to make it a little bit easier for this to hold by allowing some additional, a small power of epsilon, a small power of 2 here. So for all epsilon greater than 0, we have this inequality. So now this is a sort of thing that again answers the question that is very similar to that is very similar to what we had started with. It does apply to the case of tensors, where this boundedness condition holds. So that is nice. That was Strassen's insight. But there are many other cases where this theorem does not apply because this boundedness condition does not hold. And so I'd like to be able to treat those cases as well and to decide things like asymptotic ordering also in those cases. And so let me say a little bit about present one example, and this example is still, I think, in the spirit of tensors as well, namely representations of a Lie group, or just of pretty much any sort of thing where we can take tensor representations and that tensor product of representation should be commutative up to isomorphism. But let's go with a Lie group. So this is actually going to be a non-example because the theorem does not apply. So let's say G, a Lie group, and then let's say instead of tensors, we take representations. So these are now going to be group homomorphisms from G into some general linear group, let's say of dimension S, and another one lambda going from G into GLS. I already have too many n's around otherwise, so I don't want to write n for dimensions. So now again, obviously, we have the notion of when one representation is included in another, right? One is a sub-representation of another. We can take direct sums and tensor products of representations, and these are clearly preserve the inclusion. So these form an ordered semiring of let's say isomorphism classes of representations.
You keep G fixed, right?
Hmm?
You fix G. Can G be a finite group? That would also work fine, right? It doesn't have to be.
Like what?
G could also be a finite group.
Yes, it could be a finite group, but that case turns out to be not interesting. So basically, yeah, in that case, kind of trivializes asymptotic and catalytic ordering. So something like SU2 is an let's say a non-trivial and already kind of difficult case.
And the preorder, you say sub-representation. You could also use homomorphisms instead of sub-representation.
Well, if we take in a sense of arbitrary intertwiners, then that's not so useful since we always have the zero intertwiner. So we should require, I guess, an injective, right? And
okay.
so
that it becomes
sub-representation, or equivalently, if G is compact or reductive or a quotient representation, right? And but let's keep it with sub-representation for concreteness. That would be the ordering.
Yeah.
And so now, I mean, we have asymptotics are maybe of interest, right? As in, so now when the problem is to decide whether a large tensor power of one representation is contained in the large tensor power of another. Same type of problem as with the tensors, right? And it somehow, at least to my mind, seems like a very natural problem in representation theory. And maybe even related to, I'm not sure about things like I've been thinking, maybe it's related to quantum simulation or something. Yeah.
Just have a notation question. So this rep G is defined now as being the ordered semiring of isomorphism classes.
Yep.
And then somehow the order, like the less or equal sign, that you put into that definition.
Yes.
Before, like when you say ordered.
Yes, exactly.
Yeah, so it's sub-representation, it's the order.
But then somehow, could you just say ordered semiring of representation? I mean, for tensors, you also kind of like had taking tensors as the objects and not the equivalence classes of tensors. So do you do that?
Again, it doesn't matter. You can define it either way. And so to my mind, taking the quotient and going to equivalence class is just the same as the same thing as just using the equality symbol to denote the interconvertibility in both directions.
He wants the tensor product to be commutative.
Yeah.
So then he takes isomorphism classes to make that happen.
Yeah.
You could say, even for tensors, right? The multiplication is commutative up to isomorphism. Otherwise, yeah.
Right, but then somehow when you discuss tensors, you really don't mean elements in in the tensor, in the triple tensor product, that you mean equivalence up to equivalence. I mean, this is how Strassen.
So right, yeah, but
that is sort of like here you do explicitly, but before you did that, that's sort of like what.
as I said, again, to my mind, it's really the same thing, and there's at most a notational difference from taking the quotient or not taking the quotient, which consists of just using the equality symbol to denote ordering in both ways. Whether you use the equality symbol or a different symbol doesn't make any difference. Okay, so now the main point is really concerning the applicability of this theorem. Well, let's check this boundedness condition, and well, our unit element R1 is the trivial representation in one dimension, right? So that means R2, yeah, R2 is going to be what?
R2, sure. R1. Yeah, well, it's a dark sum of two trivial representations.
Right, so it's still a trivial representation. Yeah. And so our natural numbers and also all of these powers of 2 are only trivial representations.
Yeah.
And obviously a trivial representation cannot contain a non-trivial representation. So now this thing does not apply. But well, we still would like to be able to answer this kind of question, right? And so this is now where my version of Strassans, or at least my first generalization of Strassans Vergleichsstellensätze comes in. So maybe here I can say this is like yeah, roughly from 2 years ago. So now I need to introduce another definition briefly before I can actually state the theorem. So let me maybe just put this here. And basically the generalization consists of replacing the element 2 here in the boundedness condition and allowing that to be an arbitrary element. So if we have now just an order semiring S, then I will call an element U in S a power universal if for all A in S there exists some K such that A is less than or equal to U to the K. So it's the same boundedness condition, not just with the 2 replaced by this power universal element U. And so in the representation theory context, we can, for example, take a fundamental representation of G, or let's say, let's say if G is a matrix Lie group, then just the matrix space in which it's defined. Then it's well known that when we take a sufficiently large tensor power, we can get any other representation out of that. So that means this condition holds in that case. And yeah, in other situations, like in a more kind of quantum information resource theories sort of interpretation, this also exists in many cases, right? There often exists a state such that when you have sufficiently many copies of it, you can generate anything else that you want, like an entanglement with LS, yeah.
Just for concreteness, since you refer to this entanglement theory, what is your concrete example I should have in mind?
Yeah.
What's your main kind of example I should have in mind where hopeful maybe throughout your talks?
So for now, for the theorem that I'm about to write down here, I think the representation theory example is the best, because in that case, the theorem applies and also the homomorphisms are completely classified. And so for the representation theory thing, you actually get very concrete conditions that are for the asymptotic ordering that are basically necessary and sufficient.
And from the entanglement theory context, I should think about that. Because you referred to it several times, but I don't really know which one. Where...
So you can take, for example, a bipartite pure state entanglement. There we have the Nielsen's right with LSCC, and then we have Nielsen's theorem that reduces it to majorization. And so we're working on also the majorization case, and there but I'll say more about that tomorrow, because there, then, as I said earlier, we do not have this. So for that's the representation example.
Can you do the changes you said?
Yeah.
Can you write them?
Yes, yeah, thanks. I was just about to do that. So then, yeah, let me just write U here. So I don't want to don't have to space here. I'm running out of time, I guess. Don't have to space to say there exists a power universal, but that's what I mean. Yeah, and then in this one, the theorem is kind of still true, but I'm going to make a small modification here. Namely, I also need to allow or need to consider monotone homomorphisms that now land in the tropical reals.
Both are allowed. Both are allowed.
Yeah. So I need to consider phi's that are real valued and the phi's that are tropical real valued in these conditions. So it's a sort of disjunctive condition on phi.
Can you still keep the one greater equal component?
Yes. So this is still in here, and then tomorrow I'll present an even more general version where this is also dropped, and then that is going to be more subtle, and that's we also need to consider these Arctic things. And, but for now, it's going to be this. Yeah. So then we have this equivalence, and furthermore, we can actually say more. And this is something that we can also already do in Strassen's case. Somehow he just hadn't done it. I don't know if you knew it or not. But we can even get, sorry, now I should also put the U here, of course. We can also get rid of this additional padding here if we sacrifice the equivalence of the conditions for something a little bit weaker. Namely, so what's the best way to write this? Suppose that these inequalities are all strict. Then we can conclude something stronger than this, where we have this kind of sublinear padding by copies or by power of U. Namely, we can say that, and so now this is condition 3, that there exists a fixed k power k such that we have, what I would really like to have is just x to the n less than or equal to y to the n for all sufficiently large n. But this I don't unfortunately quite get, but at least with an additional power of u, the same power of u in both sides. Okay, and for if y is power universal itself, which is the case in many applications, then we do not even need that u. Then we really got the literal asymptotic ordering here.
So what does it mean for phi to be power unit?
Y. That's a y, no, not phi. And finally, if you thought about, for example, this in particular situations like entanglement, although this doesn't really apply yet, but let's say maybe you know that also there's this concept of a catalytic ordering, and it's closely related to asymptotic ordering. And this is also what I get at this level of generality. That asymptotic things and catalytic things are also essentially equivalent. And so there's a condition 5 here that there should be a non-zero element C. So this would be a catalyst such that Cx is less than or equal to Cy. And we can even write down a very concrete form of this, namely for some C that is of the form u to the k, and also some here basically x to the j, y to the k minus j. Yeah, so some sort of very concrete form, but maybe I'm kind of out of time now. So, but basically to wrap up, the point is that if we have strict ordering for all phi, then we got versions of the asymptotic ordering and the catalytic ordering, and this is the kind of deep result. And the converse, if either of these holds, if this holds for any n, or if the catalytic ordering holds for any c, then we certainly got non-strict ordering at the level of the phi's, right? And that is kind of the trivial part. Or if you just have this sort of thing and you apply to phi, since phi is a homomorphism, you can pull out the nth power and cancel it, and then you get a non-strict inequality here.
You get it non-strict.
So this is the usual sort of theme. And now maybe as the final thing I should say why I've called this a Vergleichsstellensatz. And so that's by analogy with these kind of scalar words are in existing use in algebraic geometry. There's, this Nullstellensatz, right? It's just this classical thing that is also, in some sense, a duality theorem for a Nullstellen referring to the zeros of the function. We have the null in there, right? So places where a function is zero. And it's also, a duality that addresses that. And then we have in real algebra, we have Positivstellensätze for order rings. So these are about where a function or a ring element is kind of positive. Then we have rings equipped with cones of elements called positive. And then again, those Positivstellensätze provide a duality theory for that. But what we have here, the situation is that we are in these kinds of conditions comparing elements. And so it's not exactly about positivity anymore, although it's very similar in flavor. But I think it's still distinct enough to warrant a different terminology. And so this is where the Vergleichsstellensatz comes from, because this is exactly saying about comparing, Vergleichen, meaning to compare elements. That's that. Yeah, and so here we have basically algebraic conditions, algebraic sort of certificates, such that when one of these holds, then we get the non-strict inequality for all these phi's. And this is kind of, one should think of this as geometrical somehow, because we're somehow evaluating x and y, two numbers, like evaluating functions. While these are algebraic certificates, but here the point is really to go from the geometric inequalities to conclude the algebraic certificates from that. Okay, I guess I should finish up for today, and then tomorrow there's going to be more applications and a deeper version of this where this condition is dropped.
A lot of time to ask questions during the break also.
Yeah, please, I'm happy to discuss, and I also hope that maybe someone will have ideas for more applications, since it's a kind of semirings come up in all kinds of situations, I guess. If you have any set of mathematical objects where you can take direct sums and tensor products, I'm interested to hear about it.